Hi again, everybody. Mr. Kolakowski, ready to go with another lesson for you. What I want to do is use this time to show you some animations, and hopefully it'll make these ideas a little bit easier to understand. Here in my background, you'll see I have a notes handout. Today, I want to focus on covering interference and standing waves. This is out of chapter 17. This is a continuation of our unit vibrations and waves. We're also going to kind of get into some sound concepts. And what I want to do is, instead of kind of writing out with my sloppy handwriting here on the OneNote, I want to show you some videos, and then what I'll do is I'll give you a blank copy of this, and then I'll give you a copy of this with some of my notes written on it. But I want to flesh out the notes with some concepts. All right, so let me begin. Over here on the first couple of topics, we see constructive and destructive interference, and we see fixed end, free end reflection, along with what a standing wave is. Let me go ahead and begin with constructive and destructive interference as a concept. I'll start this using the pen function here on the computer. So constructive interference can be described when waves are going to interact with one another, and these waves are going to have a superposition, whereby when they're at the same place at the same time, those waves, not like particles, these waves are going to overlap one another, and then after that moment of superposition, they'll kind of keep going their own separate ways. So to kind of draw that for you here, I have a wave that's been sent to the right. You could imagine it's a rope, and somebody has flicked their wrist. That wave pulse is moving based on a couple of different factors, which we've talked about in a previous lesson. And let's say on the other side of the rope, somebody has flicked their wrist, sending the wave pulse to the left. Well, what happens is when those two waves are at the same place at the same time, what'll happen is once those two waves are overlapping, those amplitude values here and here are going to add to one another to create a much taller wave during that moment that the two waves are at the same place at the same time. After that superposition, the waves will, it's kind of funny to think of it this way, the waves will just keep kind of going their separate ways. The wave that started to the right continues to go to the right, and the wave that's going to the left continues to go to the left. This is because waves are not particles. Waves have their own unique way in which they interact with each other. Destructive interference, slightly different story. Destructive interference occurs when, let's do the same sort of scenario here. We have a wave pulse that is sent to the left. That is going to with a wave that has been sent to the left, except in this case, the wave being sent to the left has, if this is a positive value, this is a negative value here in terms of its amplitude. So assuming that the magnitude of this amplitude here and here is the same, when those two waves are at the same place at the same time, superposition principle says that they will destructively interfere. In this case, it creates a null effect. Again, funny enough, after those two waves have had their moment of interaction, the wave that is going to the left will continue to go to the left. The wave pulse that was sent to the right will continue to go to the right. Again, this is very different than how particles behave. Okay, let's take a look at the next idea, but I want to show you a video for that. Here we have fixed end and free end reflection. So fixed end reflection can be demonstrated like this. Let me go ahead and open this up for you guys and give you a quick description of it. Okay, so here we have a rope, and the wave pulse has been sent left to right, and as it hits the fixed end, you'll notice that the wave the reflected wave is inverted. Okay, so if I kind of come back over here for fixed end reflection, and again, this will be written out for you guys in a file that I'll post on Canvas. But what I wanted to say there is that when you're going from a less to more dense medium, the reflected wave is inverted. Okay, to show you guys free end reflection, this can be represented like this. Let me see if I can explain that using this animation here. Okay, so here we have a wave that's been sent. You'll notice that as opposed to the previous example, because this is a free end reflection, you're going from a more to less dense medium. The reflected wave is upright. There we go, right? You can see that it's not inverted upon reflection. Okay, let me go ahead and open this up. This is what I'm kind of talking about with the less to more, more to less dense medium. Here we have the wave pulse has been sent to the right through the thinner rope, and if you kind of keep your eye on the left side of the animation, you'll see that that wave reflection is inverted. You'll also notice that the wave speed is different. Well, that's because the medium is different. We can see the linear density is different between the rope on the left-hand side and the rope on the right-hand side of the screen. Okay, this is when you're going from a less to more dense medium. Let me go ahead and contrast that with this. Here we have a wave that is sent from the more to the less dense medium, and if you keep your eyes on the left side, you'll see that the reflected wave is upright upon reflection. You'll also notice, if you're looking for different phenomena here, is that the wave changes its speed as it goes from the left-hand side to the right-hand side of the animation. Okay, so that's fixed and free end reflection. I hope that makes sense a little bit. I've got some other videos I can share with you guys. Again, I'll have the details written down for you in a PDF file that I plan on uploading for you guys. Moving forward, we have standing waves. Let me talk about these a little bit and then show you a couple of videos. Standing waves appear to be standing still. They're the result of interference. And what's going to kind of happen here is a reflected wave is going to line up and align with an incident wave. A continual pulse is going to be sent from left to right. Well, then you're going to have a reflected set of waves that are going from right to left. And as those waves interact with each other, you get, if you have the right circumstances, a standing wave. Let's go ahead and take a look at a couple of videos of this. The first one I have here. All right, let me see. This is a slinky, a large spring slinky that's on the ground. And what you can't see is there's two people. There's a person on the right and a person on the left. And what's happening is they're sending wave pulses at one another. What they're trying to do, and you can kind of see when the standing wave emerges, you get what they call nodes and antinodes. Nodes are sort of areas of destructive interference where the wave itself appears to be static at the equilibrium position, sort of at the zero amplitude. On the other hand, you have antinodes. Here you can see they're going into a higher number of standing waves. Okay, sometimes you get this random pattern. But when everything's working just right, like okay, you get those antinodes and nodes. Okay, so it'll look kind of like the picture you see here. Okay, we'll find out in a lesson to come that there's this thing called a harmonic series. But for right now, if we take a look at this, we'll notice that we have some nodes here. Again, this is a special case of interference between waves. Those are called nodes. Okay, N-O-D-E-S right here. And then you have these antinodes. And antinodes are these sort of positions of interference where the amplitudes are lined up. Again, you sort of have to imagine that this thing is in motion, like you saw in the little video clip. Okay, let's go ahead and answer a couple of questions here about this diagram. They want to know the number of wavelengths in the image above. Well, if we kind of look at this carefully, we have one full wavelength. Let me grab a different color. We have one full wavelength from here to here. Okay, that's a complete to and fro. That's essentially a complete cycle. Using a different color, we have another wavelength going from here to here. Okay, and then using one more color, we have sort of a half of a wavelength. It's not quite a full cycle. So to me, this is going to be 2.5 wavelengths. I'll use the Greek letter lambda to represent wavelength. Okay. Definitions for node and antinode, I'll put those in the PDF file for you guys. In case you missed me talking about that just a moment ago, a node is a point that is undisturbed at all times during the standing wave, and an antinode is a point of maximum displacement on the rope or string. Again, I'll put that into the PDF file for you guys. Now, if we count carefully here, let me see, I don't know, I'll stick with the red color here. We have 1, 2, 3, 4, 5. We have 6 nodes. And grabbing a different color here, we have sort of 1, 2, 3, 4, 5. Those are the maximum displacements on the rope. We have 5 of those. Okay. Again, I will label those nodes and antinodes in the image on the PDF file that I'll send out. I think what's interesting here, we could sort of ask the question, what is L equal to? Okay. Well, knowing that we have the wavelengths here, we could sort of say L, the length of this, it could be a guitar string, a piano string, it could be a jump rope. This is going to be 2.5 wavelengths, right? So if we know what the wavelength is, this also translates to 5/2 wavelengths. If we know what the lambda is, so let's say we measure the wavelength. So this is getting a little bit busy, but if I go from here to here and I measure what the wavelength is in meters, okay, I can plug that in over here to figure out the length of the rope. Okay, so anyway, that's something that we'll be looking at in a little bit more detail when we look at a harmonic series. We'll cover that another time. All right, I hope you guys are doing well. Email me if you have any questions. Again, take a look at the PDF files. I'll give you a blank copy of this along with a copy that has been sort of filled in a little bit more neatly than what I can do here on the computer screen. All right, talk to you guys again soon. Take care.